Hello dear students, welcome back to 7th week class with the Advanced Computer Organization Architecture. Here I am Aisha Siddika, Assistant Professor, Department of CSE. Today we will discuss about the design space of processor, base scalar processor, RISC scalar processor, Superscalar Architectures, and finally VLIW Architecture, which are the extended part of advanced technology processors. And that we already know in 5th class and 6th class. Let's go for today's class. At first, let's know about the design space of processor. We know the various processors families can be mapped in onto a coordinate space of clock rate versus CPI. As implementation technology involves rapidly, the clock rate are moving from low to high speed, and the another trend is that the processor designers are trying to lower the CPI rate using hardware and software approaches. Here is a design space of modern processor families. You can see here is VLIW vector supercomputer, Superscalar Scalar RISC, and the Scalar 6, and finally the super pipeline, and those are the families of design space processor. This is the base scalar processor. In base scalar processor, it is defined as a machine with one instruction issued per cycle. Here is two figures. The first one is execution in a base scalar processor, and the second one is under pipeline with 2 cycles per instructions issue. In both these figure, there is 4 steps for working. The first one is fetch instruction, the second one is decode instruction, then execution, and finally the write back. And those executions depend on the time in base cycle, and it is a successive instructions. In base scalar computer architecture, the CPU, essentially a scalar processor, consists of multiple functional units, and the floating point unit can be built on a processor attached to the CPU. Here has two portions. The first one is CPU with an attached co-processors, and another one is CPU with a built-in floating point unit. In the floating point unit, here has a main memory, and main memory is connected through the memory bus with the CPU, and the CPU is connected with input output bus system consoles by using input output bus, and here have a option of direct memory access, and finally it go to the mass storage, that means the disk step units. And the another portion, that is CPU with an attached co-processors, is working with the main memory, and main memory is the two-way connected with the co-processors and the CPU processors, and those are connected with the input output bus system subsystems, and finally it go to the mass storage. In RISC scalar processor, generic RISC processors are called scalar RISC because they are designed to issue one instructions per cycle, similar to the base scalar processor. Here is 4 working steps. The first one is fetch instructions, decode instructions, execution, and final one is the write back. And the figure is showing the execution in a base scalar processor and depend on the RISC scalar processor. In theoretically, both RISC and 6 scalar processors should perform about the same if they run with the same clock rate and with equal program length. That means the RISC and 6 scalar processor should the same performance when it maintains 2 conditions. The first one is they run with the same clock rate, and the second one is with equal program length. Without a high clock rate, a low CPI and good completion support, neither 6 nor RISC can perform as a design. And now Superscalar architecture. If one pipeline is good, then two pipelines are better. Now, this is the tagline for Superscalar architecture. For example, consider the following architecture. There is the dual 5-stage pipeline with a common instruction phase unit. Here the single instruction phase unit phase pair of instructions together and put each one into its own pipeline, complete with its own ALU for parallel operations. The main pipeline, U pipeline, could execute an arbitrary Pentium instructions. The VP pipeline could execute only simple integer instructions and also one simple floating point instructions. If the instructions in a pair were not simple enough or incompletable, only the first one was executed in U pipeline. The second one was then held and paired with the instructions following it. So, in this Superscalar architecture, there is two pipelines. One is U pipeline and another is V pipeline. Here is an example of a Superscalar processor with 5 functional units. It is possible to have multiple ALUs in stage S4. Most of the functional units in stage S4 take longer than one clock cycle to execute, and stage S3 can issue instructions faster than the S4 instruction. Here has total 5 stages. The first one is an instruction fetch unit, the second stage is instruction decode unit, and the third unit is the operand phase, and the fourth stage is ALU load store floating point. There is take more time or more clock cycle than one, and in 5 stages this is the write back unit. Here is a Superscalar processor of degree m equal to 3. In a Superscalar processor, multiple instructions pipeline are recurred. That implies that multiple instructions are issued per cycle and multiple results are generated per cycle. Superscalar processors are designed to exploit more instructions level parallelism in user programs. Only independent instructions can be executed in parallel without causing a wait state. The instruction issue degree is a Superscalar processor is limited to 2 to 5 in practice. The effective CPI of a Superscalar processor should be lower than that of a generic scalar RISC processor, and the given example is the Superscalar processor of degree 3. That is the architectural design of a typical Superscalar RISC processor architecture. Here is an example of Superscalar RISC system that is introduced in 1990. There are 3 parallel functions unit. The first one is branch processors, fixed point unit, and the floating point unit. The branch processors can arrange the execution of up to 5 IPC. It is hardwired rather than microprogrammed control unit. This system uses a number of white buses. This will provide the high instructions and data bandwidth required for Superscalar implementation. This system design is optimized to perform well in numerically intensive scientific and engineering applications. The power architecture of IBM RISC system 6000 Superscalar processors is an example of IBM RS. And this is the last topic of today's discussion, that is VLIW architecture. VLIW means very long instructions word architecture. This architecture is generalized from 2 concepts. The first one is horizontal microcoding, and the second one is Superscalar processing. A typical VLIW machine has three features. First one is instructions worth 100 of bits in length. The second one is multiple functional units, and the third feature is common large register file shared by all functional units. Here is the two architectural design. The first one is a typical VLIW processor and instructions format, and the second one is VLIW execution with degree 3. Here we discuss some similarities of VLIW and Superscalar processor. In normally VLIW machines behave much like Superscalar machines with three differences. The difference are the decoding of VLIW instructions is easier than that of Superscalar instructions. The second one is the code density of the Superscalar machine is better than when the available instructions level parallelism is less than that exploitable by the VLIW machine. The third one is a Superscalar machine can be object code compatible with a large family of non-parallel machines. On the contrary, a VLIW machine exploiting different amount of parallelism would require different instruction set. VLIW advantages. The main advantages of VLIW architecture is its simplicity in hardware structure and instruction set. And the another advantage is the VLIW processors can potentially perform well in scientific applications where the program behavior is more predictable. That's all for today. Stay tuned for the next class. Thank you.